This is EE597 with Professor Krishnamachari on Monday, June 6, 2016.
Okay, so let's resume. I wanted to make a couple of announcements. First is that there is no class on Monday, which is June 13th. So basically next Monday there's no class. And then on Wednesday, we'll have a special lecture focused on doing simulations. So how many of you have used NS3? Is that something that showed up in any earlier class? Yeah. Which class was it? 450, so you saw NS3 there, excellent. So specifically for this class, we're going to use NS3 for doing some simulations of medium access. And then later in the class, there might be an open-ended project where you could choose to do some network routing type of simulations as well. So in 450, what did you do in NS3? What was the simulation about? Do you remember?
It was just an overview of how to use NS3.
How to use it. Okay. This particular lecture next week, which will be conducted by our TA, Young Long, will be specifically about simulating 802.11, a MAC protocol. And then in class, we're going to cover either on Wednesday or the week after that, we're going to cover how to do mathematical analysis of 802.11, and you'll compare the math analysis with what you get with simulations. So he will post some directions on what you might have to install, and you'll be asked to bring a laptop if you have it, or at least share one with another classmate in class, so you can do some activity in class. But there is no class on Monday, June 13th, but on the 15th, there's not a regular lecture, but one that's focused on simulations, okay? So getting back to what we've been talking about so far, so we've really just focused on the file layer, many aspects of the file layer, everything from how to communicate to how to model channels to how to improve the communications by exploiting diversity, spread spectrum, coding, and so on. And the purpose of all of that is to at least recognize what makes a wireless network fundamentally different from wired networks, which is that the channel itself has a lot of randomness associated with it, has these fading effects associated with the multipath communications, and that the performance ultimately is both a combination of what environment you're in as well as what the communication scheme itself is. And so over the past 20, 30 years, as our cellular networks in particular have matured, as our Wi-Fi networks have matured, new link layer technologies like Bluetooth, Zigbee, and all of those have been developed, we've been trying out a number of different physical layer modulation schemes, different types of ways of combating intersymbol interference, whether it is OFDM or using spread spectrum, or there are other techniques that use equalization, different ways of dealing with the dynamics of the channel, the fact that fading comes in bursts sometimes. How do you handle that? The use of error control coding. So all of these things have been developed, but one main thing to take away is that there's always a trade-off. Right? That you don't get performance at the file layer for free. Even though your techniques might be getting better and better at achieving better trade-offs, typically there's always this power, error rate, and throughput trade-off that shows up in many guises in wireless networks. And so, for example, if you're moving farther and farther away from a base station, right, so here's a base station, here's a receiver, then because the channel is going to get more and more attenuated, your receive power is going to be smaller, so effectively you're losing power. And if you're going to be losing power, you're going to have to deal with that. That's going to cause trouble, right? If you keep your throughput fixed, it's going to cause your error rate to go up. Or if you want to keep your error rate fixed, then you're going to have to reduce your throughput, right? So we can't simultaneously get both low error rates and high throughputs out of these systems. So sometimes, though, in these networks, what you might be able to adapt is the power itself. Okay, and sometimes then the question is, how should you adapt the power? How should you choose the power so that your overall system performance is as good as possible? So we're going to tackle these questions of how to choose or set power levels in wireless physical layer as well as at the link layer. So this is sort of the topic we're at the moment. So power control and power allocation. So in certain types of wireless networks, such as systems that have OFDM subcarriers, they could potentially be used for one or more users. If you have many users where you have a certain OFDM system, you have many different subcarriers being allocated to different users, that's called multi-user OFDM, or it's called a single-user OFDM. But conceptually, the way to think about OFDM is that you have a certain channel, like let's call it the total spectrum. And what we're doing is we're splitting into smaller and smaller portions, each of which is called a subcarrier. Okay. And part of the design choice is how many subcarriers in each channel of OFDM do you have. And the phrase OFDM, remember, refers to orthogonal frequency division multiplexing. This is OFDM. So frequency division multiplexing is very easy to understand. What we're talking about here are different frequency channels. This axis here is frequency. But the occupancy of this frequency, these different subcarriers they're chosen in such a way that any signal you're sending on one subcarrier is not overlapping with the signal sent on a different subcarrier. So that's the sense in which these subcarriers are orthogonal. Okay, so this phrase orthogonal sometimes throws you off. Personally, when I first heard it, I kept getting confused about why bother calling it orthogonal. I mean, if they're on different subcarriers, why would they not be orthogonal? But I think the reason they were emphasizing this was that when this technology was being developed, it was seen as an alternative to CDMA. And in CDMA, you're occupying a larger spectrum. There are multiple users using that spectrum, but they are all on the same spectrum together. So in CDMA, the orthogonality comes from the code. Here, the orthogonality comes from the frequencies. So it's orthogonal frequency division multiplexing as opposed to orthogonal, say, code division multiplexing or something. So I think that's the sense in which this phrase is being used. And it may have been a marketing term because in CDMA, if your codes are not perfectly orthogonal, they may cause a little bit of interference between users. Whereas in theory, at least, if your transmissions on each frequency are, kept within that subcarrier, they really should not interfere with the other carrier. Now, in practice, even that's not entirely true because anytime you're actually sending a signal over a certain frequency range, there's typically some side lobe, some residual bit of leakage of the power from one portion of the spectrum into others. So it's not 100% orthogonal anyway, but those may have been reasons for it. So imagine now that you have a bunch of these channels and you're trying to decide how much power to allocate to the signal being sent on every channel. Now, that's not an obvious question to ask because maybe the obvious way to set up a system or intuitive way to set up a system might be just to use the same power in every channel. Like, why should you transmit at a different power in different channels? But this is the question that is considered in a problem known as maximizing the sum throughput over parallel channels. So the problem is we want to maximize the total throughput, which I'm going to call rate. So this is going to be the throughput for the ith channel. Well, how should I maximize my throughput if my particular communication scheme is under my control? I want to choose it in such a way that I maximize this rate for each channel. What would be the strategy to maximize the total throughput? Intuitively would be make each channel as strong as possible. Right? Well, if we had infinite power, we could make each channel infinite rate. Because we know from, for example, Shannon's capacity, right? This is in additive white Gaussian noise channels, that the rate on any given channel is going to be something to do with the bandwidth of that channel times log of 1 plus SNR on that channel. And in this term, the SNR can be controlled at transmitter. How can we control the SNR at the transmitter? By changing the power, right? By setting power. So Shannon's capacity tells us that in any channel, we can get as high a rate as we like. Really, there's no limit to it. So long as I can keep boosting my SNR. And the way I boost my SNR is I change my power level. So let's rewrite that one more time. So keep in mind, we're trying to do this. And then at each channel, the rate is log of 1 plus SNR at I. And there's some bandwidth term up front. I'm going to, from now on, kind of ignore this term for a couple of reasons. One is that this is going to be assume it's constant for all channels. And moreover, let's just normalize it to be 1. What I mean by saying normalize it by 1 is that if that spectrum has a certain bandwidth in kilohertz or megahertz, imagine that's all being normalized to say 1. That's the same as saying I'm dividing both sides by WI. I'm just measuring my rate in so many bits per second per kilohertz or per megahertz. Right? So it's just all we're doing is scaling the rate to be in terms of per unit bandwidth. So if I kind of ignore that term, what I'm left with here, this log of 1 plus SNR, I can rewrite that as 1 plus PT over PT times GI over NI, where PT is the transmit power. Let's call it PTI. PTI is the transmitted power on channel I. So now I'm using the word channel to mean subcarrier for OFDM, but in general, any parallel channels. GI is the gain on channel I, i.e., what I'm receiving is P transmitted times gain. Right? So we're rewriting what is the receive power as basically the transmit power times the channel gain. And NI is like the noise power on channel I. So PT times GI over NI, that's the SNR. Right? I can't change GI, that's a channel condition. I can't change NI, that's the receiver noise, but I can change PTI. Right? So if I want to maximize this rate, if I just left it like this, the answer is set the transmit power to infinity on all the channels. Right? But clearly that's awkward. That's not what you would like to do. And in particular, you may have flexibility to choose different amounts of powers on different channels, but the total amount of power that you have at the transmitter is going to be capped. Because it's a real piece of electronics, there's only so much power it can transmit at. Your power sources connected to your base station are going to have limits and so on. So there's no way that you can just arbitrarily set your power level to be like, as large as you want. So given that, there is a constraint that we must respect. So we want to solve this optimization problem, but we want to respect this constraint that the sum over all channels of the transmit power is no more than a P total. Okay? So in this case, the problem's a little bit more constrained than we thought. So it's not that we can choose every channel to be as strong as we want. We can do that by allocating power level, but we must meet this constraint. Okay? And again, a possible solution that you can always try is to set PTI equal to some PT for all I. Right? In which case, if you have channels going from 1 to n, then the amount of power that you transmit on the ith channel would have to be P total over n. In other words, this is what's called uniform power allocation. Okay. So you could say I'm going to just make every channel the same power, and then I'm going to transmit. I'll get a certain SNR in that case, and the log of that SNR is going to be the rate for that channel. I'll just add that rate for all the channels. That'll be the total rate I get. The question is this the best you could have done? And the answer turns out to be no. Okay. If you remember last week, we were talking about diversity combining, and we said, when you're getting these signals on different branches at the receiver, should we just combine them, with equal gain? And you can do that, but it turns out not to be the optimal thing to do. The optimal thing in that case was to scale each gain with respect to the received signal, and that gave you the best total SNR. In the same way here, it turns out that for all these different channels, it's not a good idea to give them all, it's not in general a good idea to give them all the exact same power. Okay. You want to give different powers to different channels depending on how good or bad they are. So let's think about that for a second. Look at this curve over here, log of 1 plus PTI GI over NI. Imagine, consider 2 channels, okay? So imagine you have to split your power between 2 channels. And for each channel, so let's say channel 1, I In the x-axis, I'm going to increase my power that I allocate, and in the y-axis, I'm going to measure the rate that I get. Right, so this is Ri, and this is the power. So the functions we have are all this log of 1 plus SNR type of functions. They look like this. Okay. Now, in this curve, the shape of the curve, how quickly it rises up, will be a function of that term. So this curve is basically log of 1 plus PTI GI over NI. So this term over here defines how good the channel is, and that's going to affect how this curve looks. If I have a channel that's really good and a channel that's really bad, a channel that's good for the same power, I won't get such a big penalty. In other words, so this is a bad channel, this is a good channel. On the good channel, this term is not very large. On a good channel, the attenuation, sorry, I take that back. On a good channel, the GI is large and the NI is small, so that this coefficient is larger. So you get most of the transmitted power at the receiver. There's relatively little noise, so it has higher SNR. Right? On the sort of bad channel, this term, the gain itself might be small because maybe it's a farther away receiver, and so your overall gain is small. Maybe it's in a bad fading environment. And also the noise is going to be higher. So if either of those or both of those conditions hold, this term is going to become smaller. So for the same amount of power, it's going to have a lower rate. Right? So imagine sort of drawing a vertical slice here. What your total rate is going to be is a function of GI over NI. So if the GI over NI is small, then it's a bad channel. And GI over NI large, that's a good channel. Right? So GI over NI sometimes is called the gain to noise ratio. It's basically the signal to noise ratio except for the transmitted power part. Everything else about the channel. It's like, this is the part that you cannot control. It's part of the channel. This is the part you can control yourself. But the point is that in a bad channel, as you increase your power level to try and compensate for it, the curve itself is sort of a lower curve. So now let's rethink our problem where we want to maximize sum rate such that the sum of PTI is less than equal to P total. So this problem we want to solve says, I want to choose, I have a certain total power budget. I want to choose where to invest my power. Should I put all of it on the good channel? Should I put all of it on the bad channel? Clearly not. Should I put the same amount on both channels? What else can I do? What should I do? Right? And when I present this problem, I always like to use an analogy to, well, basically life in general. Right? So you have many interests, you have many classes you might be taking, but you have a scarce resource. What is that scarce resource? Money, maybe. What else? Time. Let's focus on time. So you have a finite amount of time each week. You could spend some of that watching movies, playing video games, browsing the web, attending class, solving problems, talking to family, and you have to split your time. Let's make this problem a little bit easier, and let's just focus on your schoolwork portion of it. Let's say you've already decided, based on all of your interests, that you're going to allocate no more than 30 hours a week to schoolwork. But now you're taking 3 classes that semester. There's an OS class that's really hard. There's a 450 class. There's a 503. And you're taking all 3 of the same semester. And you have that finite budget of 30 hours to spend on these 3 classes. Right? So one approach would be you spend exactly 10 hours in each class. A different approach might be for some classes, give more time, and for other classes, less time. What's the right way to solve this problem? So the analogy here is that imagine this x-axis is time, and the y-axis is something you care about as a return of your time, some kind of a return on investment, right? So if I simplify this to the class setting, maybe it's your likely grade. That could be this axis, okay? Now, for some classes, the curve might be lower than for others. Why might that be? Can you imagine a class where you put a lot more time, but the improvement in grade may not be as high as in a different class where for the same amount of time you get a higher return on your time investment? So if you can kind of imagine, depending on each individual, these rankings might be different, these curves might be different, but you can sort of conceptually imagine there's such a curve. What is this curve saying? First of all, notice that it's kind of a concave curve. It says that you get improvements in your grades, but at some point you get diminishing returns. Like if you spend, 30 hours on one class, spending 31 hours on that, like one more hour on that class is going to buy you less than the first hour you spent on that, doing the work for that class. So this additional gains get smaller and smaller and smaller. Right? In economics, this is called the law of diminishing returns. That many things in our life, the more we, kind of invest on it, the return we get for that additional investment gets smaller and smaller. So, kind of describes these types of concave curves. But the question, though, that we're asking here is reasonable. So if we can model our return on investment as these concave curves, and the x-axis is time, we have a time budget, and we want to maximize our total return, maybe your sort of total grade across all of these classes, your GPA, right? That's what you want to maximize. Okay. So solving this problem will tell you exactly what the optimal solution would have been, if you know what the curves are. So in this case, we know what the curves look like because we know the capacity. Sometimes that's the problem, is you don't even quite know what the curves are. But you might have an intuition. You might actually know that in this class, spending my 1 hour versus 2 hours versus 3 hours, this is what I'm likely to get out of doing that much effort, whereas in this class, what will be the return on that same time? For example, in an OS class, if you only spend 2 hours working on a problem set that required you to turn in a fully functional code, and in 2 hours or 3 hours you can't even finish that piece of code and really needed 5 hours, then your utility curve looks different for that class than for another class where you might be able to do a certain number of problems in 2 hours versus 3 hours, and there's a different trade-off involved. And so, whatever these curves are, that's what you're walking in with, and you have to try to figure out what's the optimal solution. So that's the problem we're solving here. So, in optimization theory, solving these types of problems with inequality constraints, you use a technique known as the method of Lagrange multipliers. And let's write that one more time. So maximizing sum of rates, which we said is the same as maximizing log of 1 plus pt gi over ni, subject to, let's call this pti, such that pti summed over all of these n channels is no more than p total. Right. So notice that this is, first of all, a multivariable optimization. Meaning the number of things that you can change are not just one value. It's not like an f of x whose maximum you're trying to find is like x1, x2, x3, and so on. As many power values as you have channels. Right? So these are your unknown variable. Right? Design variable. That's what you're trying to optimize over. And there's a constraint on that variable which says that whatever numbers you pick for these values, they must add up to be no more than the total power. So the way we'd normally solve problems like this, if you're given a problem that's like maximize the sum of, not even sum of, let's just say, maximize some function of x1, x2, dot, 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 up to xn, such that some other constraint related to these is satisfied, right? So this is the type of problem which is multivariable optimization problem with a constraint or with constraints. Because in fact, there's another set of constraints here which is not explicitly written out here, but that basically says that all of your power levels need to be positive. So a solution in which you put a negative power level, that would not be acceptable. So in fact, there's also this constraint. Right. And so, yeah, you might have not just one of these, but you might have like a whole bunch of these. Right, I goes from 1 to, I don't know, m. You may have m different constraints. And you want to solve this optimization problem and find the answer to it. So if you go back to your undergraduate calculus courses, almost certainly you must have been introduced to the solution of such problems, and the technique of Lagrange multipliers would have been introduced in that setting. I'll give the general idea here, and I'm going to skip some details. We might come back to those details later because you might need them to work out some homework problems. But let me give the general idea first. Okay. So the general idea is that you have, when you want to solve a problem like this, what you would like to do is to define something called a Lagrangian. And this Lagrangian is a function of your design variables, the set of x values, I'm calling the vector x, and some new variables that are typically some kind of additional variables. So these are original variable, and these are called Lagrange multipliers. And then the L function itself is called a Lagrangian. And you define this as basically your f function, which only depends on x, minus the summation of lambda I gi of x minus c. So what have we done? We've really taken this problem with an optimization and a constraint into define a new function which depends on the original variables plus a new set of variables, but now there are no constraints. The constraints in some sense have become part of the original function, but with these additional unknowns. And what you do is you try to maximize this function. So, in our case, there's going to be one of these multipliers for the overall constraint for all of the powers, and then there are going to be a set of constraints for ensuring that the transmit power levels are greater than or equal to 0. So there's one constraint for each of these. There's n such constraints, and there's one more constraint here. So the number of total constraints is n plus 1 in our problem. And so we're going to have n plus 1 additional multiplier variables. And the way you maximize this Lagrangian is you find a set of points that satisfy something called KKT conditions. And these KKT conditions basically specify things like, the derivative with respect to all of these at the optimal point must be 0. All of the,
excuse me,
sorry.
in that equation you told there are n plus 1 Lagrangian multiplier variables.
In our particular optimization problem, we have one constraint here, which is the total constraint, and these will be n additional constraints. So there will be a total of n of these constraints plus one constraint from here. So this is in that set 1 to n. Then other conditions would have to do with the fact that each of your constraints must be satisfied at the optimum point. So what we're trying to do when we solve this Lagrangian is we're trying to find a set of values for your original design variables plus a set of values for your Lagrange multipliers, and they must satisfy, certain statements. And then there are a set of conditions that either lambda I equals 0 or gi of x, lambda I star, x star must be equal to the ci. These are sometimes called complementary slackness conditions. So there's a set of conditions that the optimal point must satisfy. And I'm going to skip the details right now. We'll come back to the actual details. But at this point, what I want you to take away is that when we have a problem like the one we want to solve, there is a technique that is relatively well understood, although maybe not quite so trivial, but it's relatively well understood that we can apply to compute the optimal point. But the way you do that is to use this technique called Lagrange multipliers. And it works by taking your original problem and the constraints and converting that into a single problem with no constraints, which is to maximize this new function. But this new function has a bunch of additional variables than the original ones you started with. And these new variables are called Lagrange multiplier variables. And just like when you're trying to solve just an unconstrained problem, you would try to set derivatives equal to 0, the first derivatives to be equal to 0, to find the critical point and say that's the point at which my function reaches a maximum. We do something very similar here. You set all the derivatives with respect to the original variables equal to 0. In fact, you're also setting the derivatives with respect to lambda I. So here I should have just said xi. Lambda I, at the optimal point should also be set equal to 0. And in fact, that's the same as this statement. I'm sorry, that's the same as this statement down here. Okay, and we'll come back to that. So I realize things are getting a little bit messy and complicated on the page here, but I just want you to keep for now the big picture. The big picture is there is an approach by which we can solve these multivariable optimization problems with constraints. At the end of all of that, what it gives you is basically a recipe for how to find the answer. How you find the answer is you take the derivatives of this function that we can define with respect to xi, and you know that the statement must hold, and then you put all of these pieces together and you say, what is the solution for all of the original variables plus the Lagrangians that satisfies this condition? And for our problem, you end up with solution known as water filling. And let me explain what the solution looks like. So what I've skipped today are the details of deriving the solution. But for now, just take my word for it that there's this process, and at the end of the process, there's a solution we'll end up with. And then we'll go back and look at the details of the solution later. So you have a certain set of channels. Let's just take 4 channels. Okay. Imagine that you plotted for each channel, kind of with this box plot. For each channel, the higher this value is, the higher their noise level is. It's basically a way of saying that this is a noisier channel. And in particular, the height of this channel represents the inverse of the gain to noise ratio. So in this case, it will be the noise to gain ratio. So this would be like N3 over G3, and 2 over G2, and 1 over G1. And what you do is you start, let me describe the final solution. So the final solution that you get for this problem looks as if you're pouring water into this kind of two-dimensional object, where, because it's water, wherever you pour it, it's going to have a certain level. Okay, so imagine that this is the water level. And the water level is such that it's the sort of the same across all the channels. The height of that water level from the top of this bar, right, which represents the amount of noise you have, this represents the amount of power allocated. So in particular, on these channels over here, so channel 1, this noise bar is so large that if this was going to be the water level, there is no power allocated to this channel. Its noise is simply too high. On this channel, you're allocating this much power. On this channel, you're allocating this much power. On this channel, you're not allocating, in this particular example, any power at all, because it's the same as the height or a little bit below. So how much total water do you have? What defines the water level? Is it's defined by the total power that's available. Right? In other words, how much power you allocated to this? Let me use a different way of hatching this, maybe. Kind of imagine this water as vertical stripes. So on this channel, you allocated a certain amount of power. On this channel, you allocated a certain amount of power. These two must add up to the total power level that you have. And subject to that total power level, you're allocating it in such a way that it forms a common water line across all of the channels. So we're looking at this visually, and let's first take away some intuitions about what it means visually, and then let's write it down, try to write it down as an expression, and then try to look at what's happening as you increase the total power available. So first of all, visually, right, channels that are really bad, right? In other words, have a high noise to gain ratio, may not get any power at all. So that's one thing you can observe. So that's this example. This channel has a very high noise to gain ratio. It's so noisy, its gain is so low. In this particular example, it got no power allocated to it at all. And then if you look at these two channels, the noisier channel got less power allocated than the lowest noise channel. Right? Well, first of all, multiple channels may get allocated power. Okay? And in particular, these power allocations may be unequal in general. And 3, the least noise channel gets the highest power. So if you were to sort all the channels in terms of how good they are, the channel that's the best will get the most power, the second best channel will get the second most power, the third best channel will get the third best power, and so on in general. Okay. So that's one thing you can see visually from the way this solution is described. And if your total power increases, so let's say I have a certain total power budget, and that's all I could do. imagine if for whatever reason I have double the power available to me now. Now I have more power to allocate. Then I can raise this water level further, right? So increasing the total power available is equivalent to raising the water level. Okay. So what can happen? Let's just look at that picture again. So let's say this was our original picture. This is how much power we had to allocate originally. Okay. So a certain amount of power goes into this channel, a certain amount of power is going into this channel. Now if I have more power to allocate for the exact same setup, so you have this much power to allocate, again, so this is more power, P total. What used to be just this much level, meaning if I added up whatever this height was plus this height, that's how much power I had here. Now I have more power total, meaning if I add this height and this height and this height, that's a bigger total amount, right? But now notice that when I have more power, some channel for which I was not giving any power at all now starts to get some power, right? But it's still the case that the best channel gets the most power, the second best channel gets the third best power. In this case, the third best channel gets, second best channel gets the second best power, second most power, and so on. So in this case, so far, channel 1 still has not received any power. But if you were to keep pushing this, maybe eventually, if you have a lot of power you're willing to allocate to your channels, then you can kind of imagine this picture will get even more dramatic. So it might actually reach a point where you have enough power to even start allocating to your channel 1, right? So right. So, and as you allocate more and more power to each channel, its rate is getting better. We know that from the original Shannon's equation. The more power you can put in, that log of 1 plus SNR is going to go up because SNR went up, and so you're going to get more rate. And so certainly as you have more power to spare, you're increasing the overall rate. But when you have a certain amount of power to spare, this is telling you the amount you should spare to each channel. The way you do it is you kind of plot the noise to gain ratios, and then you fill up to a certain water level, right? And you choose the water level in such a way that the total sum of all of these heights adds up to your available total power. So that's sort of the water filling solution. So algorithmically, this can be implemented by a greedy allocation strategy. And you can imagine that for now, say power allocation at each step is discretized to be some delta P, right? And basically the greedy allocation strategy would be allocate the next delta P to the channel which yields the highest additional rate. Let's call it delta Ri. Okay. So what do I mean by this? Let's go back to our example over here. So when you start over here, you haven't allocated any power yet. You're trying to figure out which channel to send the first unit of power, like first small delta of power. You want to put it in the channel that's going to give you the higher rate, right? So maybe you pick this channel. Maybe for the next time step, you'll say which channel to pick. You'll say even here, the slope, and that's really what we're talking about, is we're talking the derivative of this rate function, is higher maybe for this channel. But eventually, after I allocate enough power to the good channel, its additional rate is starting to get smaller and smaller and smaller and smaller. This is the law of diminishing returns. The slope is getting smaller and smaller and smaller. At some point, it's going to happen that the slope for the bad channel early on is higher than the slope for this good channel later on. In other words, a good channel that already has a lot of power is going to give you a little bit less additional rate than the bad channel which has very little power in it currently. So at some point, it becomes to your advantage, even if you're just greedily allocating units of power, to pick the worst channel to give the additional power level to. Does that make sense? It's like early on this was the best return on your investment, but at some point the investments return are getting saturated. They're giving you less and less. And that's when you start offering something to the worst channel. And if you look at visually what the solution was doing, it has that flavor. The first unit of power I would have put into this good channel. I would keep doing this up to a point, right? Then there's going to come a point when I'm actually willing to invest some power in the second best channel. Okay? And of course, both of these will sort of keep pace with each other. And then at some point, because of that water level being the same, but then at some point, we even start putting some power into the third best channel because somehow the additional return we're going to get on that investment starts to be better in that third channel as well. And then for a while, we keep doing that for 3 channels. And then eventually, even the fourth channel starts to give us some return on the investment. So the point is that depending on how much power you've already put into a channel, the additional rate you get from it might be different depending on how good the channel is. So actually, you can implement this water filling by just imagining that you're doing some extra, like a small amount of delta at each time. So one way to kind of describe mathematically what we're doing is the power that I want to allocate to the ith channel which itself is a function of the total power, right? Because depending on the total power, I allocate different amount of power to each channel, is the water level that we're going to get, and I'm going to, for now, just call it, let's just call it L of P total. Or maybe it should just be a function, L of P total. This is the level. Minus the noise to gain ratio for that channel, right? But only if this number is positive. In other words, it may happen that your level is below the noise to gain value, in which case we don't want to give it a negative power, we want to give it 0. But if it is that the level is higher than this number, then we want to give that difference to that channel. And this L of P total minus NIGI for all of the plus channels, they must satisfy if I sum this over all of the channels, this is how much power I'm allocating, they must exactly equal my P total. Okay, so this is just the level, the water level. And this is the total power. So if you look at this set of equations, it seems a little puzzling because L is actually unknown to us, right? NIGI we know, P total we know. But the claim is that if I tell you all the NIGIs and I tell you the P total, by iterating through, in fact, just iterating through this equation alone, you can find out what L should be. It's an equation in one unknown, right? And so solve this equation to figure out L of P total, And once you know from this what L of P total is, and then we know PTI for a given P total. Okay. So I hope this is not confusing you. All I'm saying is the answer depends on P total. What the water level is will be a function of P total. And because the water level is a function of P total and the transmit power is the level minus Ni over Gi, the transmit power that you should allocate optimally is also a function of P total. Right? And so we know from this process the optimal power level. And you should just bear in mind that this plus is really important because it can happen that the water level you calculate might make this term negative. It doesn't mean we're going to pour a negative amount of power, it just means we put 0. Right? So for those channels where this condition holds, you get 0, otherwise you get this. So what that method of Lagrange multipliers does when you work through all the details of it is it leaves you at this as the final answer. It tells you that the power levels which optimize the sum of rates subject to the total power being less than or equal to P total is this equation, these pair of equations. Okay. So the water filling solution in equations looks like this. So again, if you kind of visually look at what's happening, let's just take an example with 2 channels. So if my P total is a very small amount in this example, all of that power is going to go to this channel. So whatever power I pour in, I just pour it into this channel. As I get more and more power, I keep pouring into this channel, and I keep doing that until this number. So until my P total equals this gap, all of the power goes into channel 1. From that point on, my water level increases in this way that the additional power I'm going to put in is going to go equally into both channels. Right? Does that make sense? So up to here, everything goes to this channel. From this point on, they go equally into both channels. Imagine I have a third channel over here with a little bit higher power. Then up to this point, both of them will have the same additional power added. And then after this point, if your total power is even higher, then it's going to go to all 3 of these channels. But sort of from this point onwards, it's as if you're adding the additional power equally to all of the channels, right? So imagine this behavior. And now let's plot. So in this equation, we have this PTI star P total. We're going to plot that, okay, for an example that looks something like this. So if my x-axis is P total and my y-axis is PTI star of P total. So initially, all of the power goes into the first channel. And so PT for that first channel, the best channel, is equal to P total, right? Because everything is going into that channel. So up to a point, it's like a 45-degree line. Okay? So this is slope 1. Up to what point? Well, it's up to the point where P total equals the gap between how good the first channel is and how good the second channel is. Right? So it's up to that point, N2 over G2 minus N1 over G1. So long as my total power is less than that number, we put it all in channel 1. At this point, channel 2 starts to get some power. And channel 1 continues to receive power. And they both get the same amount of power. So one way to think of it now is that from this point on, all of the extra power that I put in needs to be split into 2 channels. Right? Which means that the rate at which each channel's power increases as a function of the total power is half. Each of channels 1 and 2 get half of the total power. Right? Does that make sense? So from this point on, the first channel's slope shifts from being 1 to a half. And the second channel starts to receive power as well with a slope half. So this is for channel 1. This is for channel 2. Right? And this will keep going until a certain point. When is this point reached? Well, this point is reached, if you look at this picture, when the total power that I added to both of these channels plus, how to describe this point? So first I added a certain amount of power that all went in here, then I added a certain amount of power that went over here, right? When we do this to a value that the power level has reached this height, right? So then we need to switch to adding power also to the third channel. So what is that inflection point? In other words, what is the total power when I'm at this level? There's a couple of ways you can think of it. One way you can think of it is channel 1 would have received, what is this number is N3 over G3, would have received N3 over G3 minus N1 over G1 power. Channel 2 would have received N3 over G3 minus N2 over G2 power. And the sum of these two is what total power is. So when the total power reaches this number, then you're at this point. Right? So basically, total power at this point is N3 over G3 minus N1 over G1 plus N3 over G3 minus N2 over G2. Yeah. So when the power reaches this point, so up to that point, it behaves the way we just described. From this point on, you're going to split your power into 3 streams. Each of those streams, for each delta PT that I add, additional PT that I add, will get 1/3 of that. So the slope will become even smaller. So at this point, the slope shifts even smaller to be 1/3 over 1, and then a new stream for channel 3 kicks in. Okay. And this point we just said is the point where it's N3 over G3 minus N1 over G1 plus N3 over G3 minus N2 over G2. Okay. And so on. So if you actually basically plot these functions, they are basically piecewise linear. Functions with slopes basically, depending on which channel it is, the best channel, the second best channel, and so on. But their slopes basically keep decreasing, 1/2, 1/3, 1/4, and so on. Okay. And the points at which they start to switch, they're defined by the gaps between their noise values. Okay. So if you were to solve the equation we saw before and graphically plot how much power each channel should receive as a function of the total power, it would look something like this. If I have very little power, I put all of it in channel 1. This is how much I put. If I have a little bit more power, I put a little bit of power in channel 2, a little bit of power in channel 1. If I have a little bit even more power, I put some in channel 3, channel 2, and then channel 1. So basically, how much power you're putting into each can be kind of visualized this way as well. There's a couple of different intuitive ways to visualize what water filling does. So it's a really beautiful result because just intuitively very clean to see what's happening. And in wireless networks, we use it. We actually, if we have whether it's a single user or multi-user OFDM system, if you care about maximizing the sum rate, water filling is the solution that you use. Years ago, I had a collaboration with Sprint Labs, and they had just started to roll out WiMAX as a protocol, and it was basically based on OFDM and multi-user OFDM, and they wanted to know how should they schedule the power levels for different users, and we were basically using this algorithm as the basis for doing that. Okay. So it's a very useful technique for what's called resource allocation. Right, so it's basically power resource allocation. Okay, so that's water filling. A different place where we encounter power control. So water filling kind of assumes that the additional power that you put in can be used to give you a rate improvement, right? So basically more power equals more rate. But sometimes you have fixed your modulation scheme, and now more power doesn't mean more rate, it means the same rate but a lower error rate. Right, going back to that trade-off, if you don't want to change the rate, you can also change the error rate. So here's a problem we encounter when we schedule links. And that's called the problem of power control for independent links. So the best way to imagine that is a scenario something like this. So you have a transmitter 1 that wants to talk to receiver 1. You have a transmitter 2 that wants to talk to receiver 2. And assume for now that they are fixed rate radios. Now if they're fixed rate radios, what's going to affect their performance normally is just SNR, but now there's an interfering transmitter as well. And so there's going to be some interference as well. And so the metric we care about is called SINR. And we assume that there's some gain on each link, G11, G12, G21, G22. So SINR for link 1, we say is the transmit power on link 1 times gain on link 1 over the transmit power on link 2 times the gain 2-1 plus whatever the noise is on this receiver 1. And this is the SINR. If I cannot change my rate, then by increasing my SINR, what I can do is I could improve my error rate. Or a different way of thinking about it is that there's some threshold that I want to make sure it's above, right? So I want to kind of, let's say, meet some outage condition. I want to make sure my SINR is above some threshold. Okay, so this is the desired threshold. For now, we're not worrying too much about the probabilistic world that we live in. So in fact, you know, these gains may be subject to fading. They may be random variables, in which case this itself is a probabilistic event. But for now, we're assuming that these are just instances drawn from that distribution. For now, think of them as constant. Okay. So assume GII, GIJ are constant. And one case when this happens is slow fading. So we talked about coherence times. If your coherence time is really long, there's very little mobility in the environment. You do have, you know, different links have different gains, and spatially they could reflect what the multipath looks like. But if there's no mobility, then however bad they are, they stay bad for a long time. However good they are, they stay good for a long time, right? So under slow fading, these things can be treated as if they're constants. So SINR 1 looks like this equation. We'd like that to be bigger than theta. Similarly, SINR 2 is the transmit power for node 2 times the gain on its forward link, transmit power of the other transmitter times the gain from that transmitter to your receiver plus the noise at receiver 2 must be bigger than theta. And for now, say N1 equals N2 equals N. Just the noise at each receiver is the same. Let's assume they're similar receivers. They don't have any other differences between them. So what's the question we can ask? The question we can ask is, what power should I set for T1? What power should I set for T2? Right? So our intuition from before is we should set it as high as we can. Now they're completely different links. They're not tied together. I don't have a joint power constraint. I can make each one as high as I want to, subject to some max power. So if I have a maximum power level, intuitively I should make that the maximum power, this the maximum power. The problem with that solution is that while that's good for your own receiver, it's really bad for the other receiver. So if you set your link to the maximum power and they set their link to the maximum power, and you're both, the assumption here is you're both on the same channel. So you're not physically on different channels, you're not using orthogonal frequencies or codes to communicate, you're on the same channel. And in this case, it's a bad idea for both of them to transmit necessarily at the highest power because they may interfere too much with each other. Okay. And the analogy I use for this type of a power control problem in wireless is what we do when we're having conversations with other people. If everybody in a small area were talking to the person next to them and they wanted to get the highest SNR in the absence of any interference, they should speak as loudly as possible, so then they'll be heard. But the reason we don't speak loudly in a gathering where there's lots of other people is not that it's going to be good for the person who you're talking to. It's going to really hurt the conversations of everyone else. Right? That's the sense in which we say it's rude or impolite, is that you're interfering with their communications, you're causing too much interference to their channels. So in fact, it turns out that maxing the transmit power on both of these transmitters is going to be a bad idea. It's going to increase too much the interference term. So the question is, how should I set PT1 and PT2 so that both links are happy, both of them have an SINR above the threshold? And first of all, is that even possible? Can we guarantee that such a allocation of power levels exists? Okay. And if it does exist, how do we find it? What's algorithmically the way in which we can come to such a set of transmit power levels, right? So these are the questions that arise in this problem. So let's think it through. So going back to the expression for the first one, so PT1 times gain 1, 1, I'm just going to rewrite it, is bigger than theta times PT2 times G21 plus N. This is the first equation that we have. And then the second equation says PT2 times G22 should be bigger than theta times PT1 times G12 plus N. So we want both of these inequalities to hold simultaneously. Right? For both links to be satisfied. So equation 1 is actually the equation of a certain line, and equation 2 is also the equation of a certain line. And we're going to plot these two lines and see for each of the lines, one side of it satisfies the inequality and the other side doesn't, and then we'll see what are these sides that satisfy the equations and where do they both intersect. If you have that you're on the right side for both of these lines, that's the place you would like to be. So imagine we were plotting and my two axes are PT2 and PT1. So I'm going to write equation 2 first. So equation 2 says PT2 times G22 is bigger than this number. I'm going to rewrite all of this as PT2 is bigger than theta times G12 over G22 times PT1 plus theta n over G22, right? So now you can see it's an equation of a line, because think of this as y, think of this as x, think of this as some a and some b. This is the y-intercept, this is the slope, this is y versus x. Right? So this is an equation of a line, or a linear inequality. So if I said that equal to 0, it would be a line. Greater than means it's on one side of the line. Everything above this line. And when the transmit power for the first one is 0, then we just need the transmit power for 2 to be bigger than theta n over G22, right? Which, if you think about that for a second, just says that the SNR needs to be above the threshold. So this is the threshold. So if there's no other interferer, you just need it to be above n over n theta over G22. And then from this point on, this is that line. And the slope of this line is this number over here, theta times G12 over G22. So what this is saying is, if there's no other interferer, I need to make sure my power for this link is above this point. As the other node starts to transmit to its receiver, it's causing interference, and to deal with its interference, I'm going to have to boost my power level higher and higher and higher. The minimum value it can take on gets higher and higher and higher. Right? Everything above this, receiver 2 is happy. Okay? So in this entire region over here, receiver 2 benefits. What does it look like for the other equation? So if I write the other equation, I can write it like this. PT1 is bigger than equal to, there's a similar expression, theta times G21 over G11 times PT2 plus N theta over G11. Okay, so this is what comes out. So again, it's another line, but now we've reversed the axes. This has become the dependent variable. This has become the dependent variable. This is the independent variable. And so this is the slope of that line of PT1 as a function of PT2, and this is the y-intercept of that line. So imagine kind of what we did here, but like with this figure kind of rotated and maybe even flipped if you prefer to keep the right quadrant. And in this curve, it's the same idea. There's some, see, if there was no interferer, there'd be some power level at which PT1 would be high enough, which is the SNR would be above threshold. And so this point would be N theta over G11. And as I increase interference to it, there's going to be a need for the first transmitter to boost its power higher and higher to stay above threshold. Right? And so if I have it kind of, I don't know if this is flipped in a way that's convenient for people to see, but let's kind of make this face up, if I can. Let's see. Okay, good. So, so as this is facing up now, imagine what's happening is basically the same figure we saw before, except now we want to be high in this dimension, so we would like to be anywhere down here. Right? So before we said anywhere above this line in this direction would make receiver 2 happy. Now anywhere above this line in this direction makes receiver 1 happy. So if we want both receivers to be happy, we have to line the intersection of these two regions. Where is that region? It's this triangular area. Right? Because in this triangular area, you're above this line in this dimension, and you're above this line in this dimension. Right? So this is the feasible region for both receivers. Now, the slope of this line needs a little bit of care. If I write it in this way, the slope is theta G21 over G11. But actually, what I want to say is maybe the slope in our standard axis, if I can bring it back here. So in our standard axis, this slope is the inverse of this slope. Right? Because now I want to say PT2 over PT1, which would be G11 over theta G21. Right? So long as we set the power levels high enough for, high enough. If we set for both PT1 and PT2 in such a way that it lies in this region, both receivers will be happy. If I'm too high up above this region, what ends up happening is receiver 2 is happy, its power level is good, but you've caused so much interference for the second receiver that it becomes unhappy. Likewise, if I operate over here, then receiver 1 will still be happy because you're sufficiently high above its curve, but you've dropped, you've kind of caused too much interference to the other receiver. Right? And so this is the region in which we want to operate. Couple of things to note. Intuitively, this point or close to this point is a good, close to here is good to operate. So one question is why? We just said you can operate anywhere in this region. Why is this part more preferable? You can save power, right? So in this case, because in this case, both PT1 and PT2 are in some sense the smallest they can be and still make both receivers happy. Okay, so this is sort of, ideally you'd like to find that intersection point and operate close to the intersection point. So two things to note. If these lines intersect, right, we can easily compute the operating point. Exactly. It's basically two lines. I give you the equation of two lines. I ask you what's the point at which they intersect. That's two equations and two unknowns. We know how to solve that. Right? Just two equations and two unknowns. Okay. But the key point is if. Could it ever happen that these lines don't even intersect? Yes. And what would that condition be? Say that again? Yeah, the slopes. See, if this slope was sufficiently high or this slope was sufficiently low, these two lines, instead of intersecting, might never intersect. Okay? So there's no guarantee that there must be a point at which the two lines intersect, because it can happen that they simply don't. Right? So what would that be? It would be if the slope of this line was equal to or higher than the slope of, so if the slope of this line was higher and higher, it gets less likely, and to the point where this slope is equal to this slope, they'll be parallel to each other and not intersect, right? Because then they'll both be like this. And then from that point on, it's all bad, right? So basically, if I call this line something, let's give these lines a label. Let's call this L2 and L1. L2 is the line for the second power level, second receiver to be happy. L1 is the line for the first to be happy. So there exists an intersection, i.e. solution, where both receivers are happy, if and only if the slope for L2 is less than the slope for L1. Okay. So what is the slope for L2? We said is, i.e. theta times G12 over G22 is less than G11 over theta times G21. So this is basically the condition you want. If this condition holds, you're good. You can find a solution to the power control problem. If this does not exist, if this is not true, then it becomes hard for you to, there is no solution. Right? So I can rewrite this expression to give us a little bit more insight. So let's look at this. These are what are called the forward or signal gains. Okay. These are the cross interference gains. This is the SINR threshold. The higher the SINR threshold, the harder. So basically, if things on the right were bigger, that's bad for us, right? So if the SINR threshold is bigger, it makes it harder to satisfy, so that's bad, which makes sense. if you want, your links are very picky about how much SINR they want, it's harder to find a solution. Likewise, if the cross-interference gains are high, that makes it hard to find a solution because they interfere too much with each other. On the other hand, if your forward signal gains are high, that's good for you because your actual signal strengths are going to be higher. So this reflects the interference, this reflects the threshold, this reflects the forward signal gain. What's interesting is that the noise power doesn't even show up in this calculation. At least if the two noise powers are equal, they cancel out, they don't even show up in the equations. If you recall, where the noise really showed up was in the intercept of the line equations. It didn't show up in the slope. What determines whether you have a solution or not depends only on the slope. The actual solution, the point at which they intersect, will depend on the intercepts. But whether you have a solution or not does not depend on the noise. Okay. So intuitively, harder to find a solution when SINR threshold is high. Oops. B, cross interference is high. C, signal gain is low. Right? So there's very intuitive statements, but this equation kind of captures all of those intuitions. So this set of equations are actually very powerful. Even if we just take two sender-receiver pairs, you can start to really study when is there too much interference, when is there not, when can you operate these links. So for example, imagine a situation that looks like this. Versus, say, a situation that looks like this. Okay. So in scenario 1, you can see that the two pairs are close to each other and away from each other, away from the other pair. In this case, the transmitter for one is talking to this receiver. The transmitter for this other T2 is situated close to the first receiver but far away from its receiver. So in these two situations, which one do you think is more likely to have a power control solution? Which one is less likely to have a power control solution? The first one is more likely to have a solution. Because here, the interference terms are going to be low, the signal terms are going to be high. Because they're close to each other, they can be strong. They're far away from the other pair, therefore the interference will be weak. Right? So then we can find a solution. And in this scenario, although it's not trivially obvious, but you can kind of see what's happening is this. Now, the cross interference from T2 to R1, this term might be really high. Okay, so this term is G21. Is going to be really very high. It's not very far from each other, so you get a lot of interference. On the other hand, the gain term, the forward gain term G11 is very low. The forward gain term G22 is kind of low. And, the other cross term doesn't really matter. It is low, but it doesn't matter so much as this term being really high. Right? And so it can happen, and of course it depends on the actual number even of the G12 term. But if you look at in this equation, what we're doing is we're boosting one of these numbers and we're dropping these two numbers. Right? And so it can happen in the second case, maybe more likely than the first case, that you don't even find a solution. But sometimes there's some very surprising scenarios that actually have power control solutions and they're not intuitive. And one such example is the following. Oh, sorry, one. So this is a scenario in which there is one link where the two nodes are close to each other, another link where the nodes are far from each other. Okay? It's really not obvious that there is a way for both of these links to be satisfied simultaneously because it feels like However loud T2 has to be to reach R2, it may be probably interfering with R1 a lot because it has to shout to be heard at R2, right? But it turns out that for this type of a scenario, surprisingly, it's actually not very hard in many cases to find a power control solution. And the intuition is that even though this gain is weak, this gain is really large. So it's like in that first part that G11 is kind of compensating for G22 being kind of weak. And T1R1 is so much higher because it's so close to it, and it's a nonlinear gain effect typically with distance, that it sort of compensates for the interference caused by T2.
Excuse me, Professor, is your 5-minute warning?
Sure. And then on the other hand, when T1 is talking to R1, it can lower its power level, since it only needs to be heard nearby, enough that it won't cause any interference to R2. Right? And so somehow, even though it doesn't look intuitively like there should be an answer, you can very often find a solution for configurations of this form. And the best analogy actually is acoustics. So if you're in a classroom, and this is your professor, and this is other students in the class, this is you talking to the neighbor next to you in class. And both communications can happen simultaneously, because you whisper at just the right volume for your neighbor to hear you, but not enough to bother somebody else, right? But that class instruction, my voice in the classroom, is typically much louder than the conversations that might be happening in between. So you're actually exercising power control every time you speak. You're trying to decide what power level to transmit at. So you're careful not to interfere with the others. The professor doesn't know that you're doing this maybe, but the point is that there's a solution in that case. So in fact, these equations for SINR that we're describing hold identically for acoustic communication. This power level could be how loud you're talking. This gain is how far away you are, the inverse of how far away you are from the person you're talking to. It turns out that acoustic waves also decay with distance roughly, let's 1 over distance square, for the same reasons that the radio signals decay. And so you can take, and there's also an SINR threshold that our ears have. So your ability to decode what someone is saying to you is a function of the SINR. This is why sometimes you're in the shower and somebody's shouting at you from the outside and you can't hear them, because the amount of interference you're getting close by is too high for you to be able to decode that transmitter. And it annoys the people outside the door a lot because they can hear you just fine, right? Have you ever experienced this? And the scenario there is you have the 2 links. So here's, let's just call them 1 and 2. And then there's a heavy interference source close to 1. The signal coming from 2 to 1 is received with a certain strength, but at this node, the interference is also very high. Whereas in the other direction, the signal might actually beat the amount of interference coming from here. Right? And so the SINR at 2 might be higher than the SINR at 1. So in that situation, 1 is able to decode, but 2 is not. And this is, in fact, an example of unidirectional link. So when you have interference that you want to take into account, different receivers might be experiencing different amounts of interference. It can happen that one node can talk to the other, but not in the other direction. So sometimes when we're deploying these low-power sensors, these are issues that we worry about. The additional interference is not a shower, it's a Wi-Fi access point nearby that's blasting away. And so this node is unable to decode signals coming from a different node, but in the other direction, communication is perfectly fine. And if your protocol assumes that if you can hear someone, they can hear you, it's going to run into trouble. Right. So the analogy to sort of real acoustic communications is a very interesting connection, and one that we can exploit when we design our networks. Builds a lot of intuition. So just to sum up, since we're out of time, today we spoke about power allocation over parallel channels and power control over 2 independent channels. Okay. We can generalize what we talked about today to more than 2 channels, and we'll do that next time. So in the first part, this is when we were talking about water filling. And with the second topic of power control over 2 independent channels, we've already gone above the physical layer a little bit. We've started to talk about the link layer. because this is really medium access issues. You have different links and they're interfering with each other. You're starting to talk about medium access, and the next topic coming up is basically the link layer and medium access. Okay. All right, we'll stop there.
This concludes EE 597 with Professor Krishnamachari on Monday, June 6, 2016.